Hi, this video is on exponential functions, growth and decay, but before we get going I just want to quick review some exponent rules. Actually, even before I talk about negative exponents, I want to just review that when you have, say, let's see, 3 squared, of course that's 3 times 3 is 9. If we have negative 3 squared here, it's important to know when talking about exponential functions that negative 3, remember, is not the base. Only the 3 is seeing the base. This is really, the result of this simplification would be negative 9, because this really is negative 1 times 3 squared. If we wanted that negative or sign to be seen by the exponent, it would have to be inside parentheses. Okay, and that would equal positive 9. So that's important to know. Okay, let's talk about negative exponents. Quick review. Example, let's say 4 to an exponent of negative 3. That has nothing to do with the sign of a number, positive or negative. That negative 3 exponent is really telling you to take that 4 and bring it down to the denominator. So 4 to the negative 3 power would be 1 over 4 cubed, which is 1 over 64. Let's take a look at maybe a fraction. Let's say 1/5 to the power of negative 3. That would be the same thing as 1 over 1/5 to the power of 3 cubed. So that negative symbol here is just telling you move this base to the denominator. Of course, this would equal 1 over 125th, which equals 125. And let's just now even look at a full fraction, 2/3 to the negative 3. That's saying 1 over 2/3 cubed, which is 1 over 8/27, which is 27 over 8. Okay. The exponent of 0, of course, regardless of the base, anything with an exponent of 0 equals 1. So whatever base we have, all real numbers, if it has an exponent of 0, it's going to equal 1. Why is that? Well, we could just look at any example here. Let's say 4 cubed divided by 4 cubed. We know that our exponent rules say if the base is the same in a quotient like that, we could take those exponents and say take the difference of them. So this is 4 to the 0. Well, 4 cubed is 4 times 4 times 4 in the numerator, and 4 cubed, of course, is 4 times 4 times 4 in the denominator. And we can just reduce all of those factors out to 1. Anything divisible by itself is 1. So that's the reason why anything with an exponent of 0 is 1. It's really just stemming from the properties of exponents. And then a very quick reminder that a fractional exponent, such as, let's say, 4 to the 1/2, that's really the square root of 4. And of course, when we say square root, really there's an invisible 2 here. We just use square root so much. We have gotten lazy in square root. We just drop that 2 there. And again, this just comes from the property of exponents. We know that the inverse operation of square rooting, say over here I'll do, so if I said the square root of 4 and the inverse operation is squaring, we know that they undo each other. So that would result in the square root of 4 times the square root of 4, which is the square root of 16, which of course is going to give you back 4. Well, the property exponents would say 4 to the 1/2 times 4 to the 1/2. Well, we know that if we have the same base in a product, that we add the exponents. And so we've got 4 to the 1/2 plus 1/2. That equals 4 to the 2/2, which is 4 to the 1. And we see we end up with the same result. So fractional exponents just again stems from the properties of exponents. Okay, let's get exponential functions, growth and decay. An exponential function is when we have some kind of base and the exponent is actually the input, x. So the independent variable is the exponent, not the base. So don't confuse exponential functions with something like this. Okay, we know that's a quadratic, for instance. So that is not what we're talking about here. We actually have the independent variable being the exponent. Okay, so let's investigate that a little bit. Here I've got some tables set up. So I want to look at a base of some positive number, and I just randomly picked positive 2. Let's look at a base of negative 2, and let's look at a base of 1 and see what happens. Okay, so the base in all of these cases on this first table is going to be a positive 2, and I picked a range of independent range of numbers for our independent variable. I went from negative 3 up to positive 3 just to see a trend. And of course, we're going to look at the base being 2, and then I'm going to substitute in these numbers, these values for that independent variable, and see what we get. All right, so we have 2 as the base, and 2 to the base of negative 3 is the same thing as 1 over 2 cubed, which is 1/8. Likewise, 2 to the negative 2, we've got 1 over 2 squared is 1/4, and 2 to the negative 1 is 1 over 2 to the 1, which is 1/2. And of course, anything with an exponent of 0 is going to be 1. And we have 2 to the 1 is 2, 2 squared is 4, and 2 cubed is 8. So here we see we're starting with 125 thousandths, moving up to a quarter, and it's rapidly growing, if you will. So that's really the essence of an exponential function. An exponential function is something that models real-life scenarios that are increasing or decreasing rapidly. This is not linear. So if we actually graphed on the coordinate plane then these values in this table that we just put together, then we're going to see this nonlinear growth up into the right curve. Okay, so what can we glean from this? We can see a couple of different things. We can see that the more and more negative this independent variable goes, so the more and more we're going to the left on the x values here, that curve is getting, that y value is getting smaller and smaller and smaller, and it's approaching 0. Okay, but it's not actually touching 0, it's just approaching 0. And as the x values grow bigger and bigger and bigger to the right, well, this thing's going off the charts. It's growing rapidly, or we would say exponentially. So this is the quintessential graph of exponential growth. Okay, now let's look at something that looks very different. We're going to investigate here a base of a negative number. In this case, I chose negative 2. Remember, if I want that negative 2, that sign to be in the base, I have to capture that inside the parentheses. So let's take a look at what these numbers look like and compare. So I have 1 over negative 2, and that would be cubed, which would equal negative 1/8. I have 1 over negative 2 squared, and that's going to equal a positive 1/4. I have 1 over negative 2 to the 1, which equals negative 1/2. And of course, everything with an exponent of 0 is 1. And I have negative 2 to the 1, which is equal to negative 2. And that's negative. Negative 2 squared is going to be positive 4. And a negative 2 cubed is going to be negative 8. Well, this looks very differently. You can see, first of all, we're bouncing between positives and negative numbers. And if I attempt to graph these, below you see a scatter plot that I put together, and it's very strange looking. I've got these points that are sort of bouncing positive and negative in a bigger and bigger way. They're just going to kind of spread out and keep going, positive and negative in this scatter plot. I cannot connect these points at all. In fact, because if you just think about any number, maybe the easiest number to think about would be an exponent of a half. So if I look at x here, right in the middle of 0 and 1, being an exponent x of 0.5 or a half, we know that's the square root. So if I attempted to take the square root, say, of our base in this exact example is -2, well, that's not real. That's not a real number. And this coordinate plane is two real number lines. The x and y axes are real number lines. So I couldn't connect these dots at all, and hopefully you can see that this is not a function. And it's actually really quite strange. And finally, let's look at the base equal to 1. Well, if I have a base of 1, then I have this -3 here being, I've got 1 over 1 cubed, which is going to be 1 over 1, or 1. I've got 1 over 1 squared, which is also 1 over 1, or 1, and so on and so forth. So hopefully you see that no matter what we do, we're going to end up with an output of 1. And if I graph that on the xy coordinate plane, then I just have an equation here, a linear equation, of y equal to 1. And so certainly this is not an exponential growth. So the long and the short of it is, I wanted to do these comparisons to show you that a negative base is certainly not going to yield exponential growth or decay. Neither is a base of 1. So let's go ahead and make some conclusions here. The base we see above, the base cannot equal 1. And the base cannot be negative, so it has to be greater than 0 in our observation. As far as the exponent or the independent variable, there seems to be no limitations in this general case here. So there's no limitations. The domain here for x is all real numbers. And finally, y. If you look at this general case here of y equals some base to the x exponent, you can see that our y is greater than 0. So we should note that y is greater than 0. And this is actually going to be very important when we talk about the inverse operation to an exponential function, which is logarithms. So this is important to note, that output, even though these exponents are positive and negative, doesn't matter. That negative exponent is just putting that base down into the denominator. So regardless, we're ending up with a positive number for the output. All right, now we talked about the base cannot be 1. It does have to be positive. What happens if the base is greater than 0 but less than 1? So let's take a look at an example where we have a base of 1/2. So here I put 5/10, but let's just write it as 1/2. It might be easier to see. So we have a base of 1/2 to an exponent of -2. So we've got 1/2 as the base with an exponent of -2. Well, that's just 1 over 1/2 squared. And that's going to equal 1 over 1/4, which will yield 4. And I've got 1/2 to a -1 base, so that's just going to be 1 over 1/2 to the power of 1, which is going to yield 2. Any exponent of 0 is going to yield 1, and then I have 1/2 to the power of 1, which is just 1/2, and 1/2 to the power of 2, which is 1/4. So if we take a look at what this curve looks like, we see that when the exponents are negative over here, we've got larger numbers, and as we're approaching more larger positive x values up to infinity, that output is going to become smaller and smaller. So in this case, our curve is not rapidly growing. In fact, it's rapidly decreasing. And we call this type of exponential function exponential decay. And hopefully you can see here that the output, I had mentioned, is decreasing rapidly. And we see that y, again here, is greater than 0, and the curve is approaching 0, but not touching 0. So we would call y equal to 0 a horizontal asymptote. Okay, so that that curve is approaching but will not touch. Likewise up here, I should have said that this y equals 0 here is the horizontal asymptote. Now, let's take a look at other examples where our function actually has some kind of coefficient here in front of it. So in this case, we have y equal, we have the same base and exponential function, but now we have some kind of coefficient in front of it. Let's take a look at what that does to the curves. So here I've kept with the same base 2. And I just want to compare what happens if we have a coefficient of 4 or a coefficient of 1/4. How do these two compare? They're both positive, but one is reciprocal of the other. Okay, rather than tediously completing whole tables here of points, it's easier to just kind of get your bearings with first looking at the y-intercept. And the y-intercept always in any function is going to be when x equals 0. So here we have 4 times 2 to the 0. Any exponent of 0 equates to 1. So we've got 4 times 1, which equals 4. And you could see our y-intercept right here at 0, 4 point. And now let's look at the exponent of 1, because that's always an easy one to look at. 4 times 2 to the 1, well, that would just be the product of 4 and 2, which is 8. So right there, just from those 2 points, you can probably sketch easily that exponential here curve and see that again the the x-axis rather, y equals 0 is the horizontal asymptote. So here, if you could look at this, the domain again is all real numbers. And the range is y greater than 0. And you can finish completing this table, but in the interest of time, I'm going to keep going. But of course, you can see this up and to the right nonlinear growth, so this certainly is an exponential function. Now, let's look at what happens if we have a coefficient of 1/4, the reciprocal. Again, let's go to the y-intercept. So we have 1/4 here times 2 to the 0, that's just 1/4 times 1, which is 1/4. So here our y-intercept is just 1/4 here. And 1/4 times 2 to the 1 is 1/4 times 2, which is 2/4 or 1/2. And that's that. And you can try some other points here. 2 1/4 times 2 squared would be 1/4 times 4, which is just 1, and you could see what we have here is this fractional coefficient is slowing down the growth, if you will. It's spreading it out to the right and slowing it down. It's a much wider curve, whereas this coefficient of 4 is increasing the growth. It's making it more rapid. Okay, so, but in any case, the domain is the same. The domain is all real numbers, and the range is the same. The range, or the output, is going to be greater than 0. Now let's take a look at the effect of negative coefficients. So here it's the only case where we can actually get negative outputs. And it's only because we're just multiplying whatever positive result. This is always going to yield a positive result, and we're just multiplying a positive number by a negative number. That's the only way we can get this negative outputs. So again, let's look at the y-intercept. We've got negative 4 times 2 to the 0, which is just negative 4 times 1. And our y-intercept would be 0, negative 4. And negative 4 times 2 to the 1 is negative 4 times 2, which is negative 8. And that would be here. And so when we just to get our bearings, when we get those 2 points, you can automatically, easily tell that we have this sort of downward curve here. And again, the domain is all real numbers, but in this case, the range had been toggled now to be negative just because of that coefficient. So y is less than 0. And in the interest of time, I think you can quickly see that this coefficient of negative 1/4, a fraction, is going to spread out the curve and slow down that decrease just in the same way that positive 1/4 did above. So if you fill out this table, you'll find that here when x equals 0, you're going to have an output of negative 1/4, and when x equals 1, you're going to have an output of negative 2/4 or negative 1/2. And so you can see that also decreases, and the domain and the range are going to be identical. Okay, one of the most popular exponential functions used in the financial world is compound interest rate, and this is a formula to calculate what your ending balance would be of a certain dollar investment that is earning an interest rate given in an annual percentage. So here A stands for that ending account balance, P stands for principal, which is the initial money invested, R is your annual interest rate. However, most of the time you're going to be earning an interest or compounding an interest on something more frequent than an annual rate. So you would take that annual rate and divide by the frequency that interest would be compounding. And then this whole base here would be raised to an exponent of that frequency rate n times the number of years that your money is in this account and earning this compound interest rate. So if we looked at an example here, you deposited $1,000 in an account that pays 8% annual interest rate. Find the balance after 1 year of interest that is compounded on a quarterly basis. So we would just use the formula A equals P, and P in this case is $1,000. And we're going to multiply that 1 plus 8%. 8% is 8 hundredths. And we're just going to reflect that as 8 hundredths in a decimal form. Divided by quarterly, interest bearing would mean 4 times a year. So we're going to divide that by 4. And then we have 4 times the number of years, and we were told that the number of years our money is in there is 1. So 4 times 1. So we have A equals 1,000. 1 plus 8 hundredths divided by 4 would be 2 hundredths. Times, and 4 times 1 is just 4. So we have A equals 1,000 times 1 and 2 hundredths to the 4th power. We would just use our calculator to figure out what that is. And we end up with 1,000 times roughly 1 and 82 thousandths, I guess. And so our ending balance after a year of earning this compound interest would be about $1,000 and 82 and I guess 43 cents. So we earn just under $83. That would be how we would use that formula. And before we close this out, I want to talk about something called the natural base E. And this E is kind of a cursive lowercase. And it's a similar kind of number that pi is. As you know, pi is irrational, but we use it so much in geometry that we've given it a name and we've given it a symbol. We have its own dedicated button on a calculator. But it is a constant. It is irrational, but it is a constant that is 3.14159 ... goes on forever. So it's a very prominent number that we use in math. And likewise, the natural base e is also used quite a bit in biological and physics and other sciences and even financial analysis. So the natural base e has a dedicated name to it, and that's the lowercase e and symbol. And it was first, I guess if you Googled, it would say it was discovered by Leonard Euler in the 1700s. I don't think of it as much as a discovery as it is that he noticed or observed a trend and the usefulness of this number, and so he gave it a name and a symbol. I think I read somewhere that Euler insisted that he did not give it a lowercase e for his own name, but he really gave it that e to stand for exponent. In any case, you can see this natural base number used all over the place. In fact, you could read whole books on this number, and it's very interesting. There are hundreds of YouTube videos that talk about this number. But maybe the easiest case to see where it arises is using the same formula above here that we looked at, the compound interest rate. If we looked at that same formula, and instead of looking at a quarterly frequency, if we speed that up and kind of look at, going faster, so quarterly down to monthly, down to weekly, daily, hourly, every minute, every second, so on and so forth, you can see that this number starts to show up. So by daily, we're at 2.71, and it goes down and down and down until you get to 2.718... And that's exactly what that natural base e is. So you can find this number as a button on your calculator, and it will be in the same location as a second button, which you'll see with it, either below or above it, ln, which stands for natural log. And we're going to talk about that in the next session. But the natural log will be the inverse operation from using this base e. And so you will see base e with some kind of exponent, independent variable x, all over different models for different things in the physical world. Okay, so that concludes this session. Hope this helps. Take care.